So today we're going to start bonds. So in keeping with the word bonds, here I have James Bond. So chemical bonds. So when we have a chemical bond, this is the attraction between the nuclei of different atoms and the valence electrons. And this attraction is what binds atoms together. So the reason why atoms do bond is because they're trying to get a full set of valence electrons, and their goal is to become stable. So we're going to go over different ways that this occurs. So if we look at the octet rule says that when compounds form, they tend to form so that each atom, by gaining or losing electrons, has an octet. That means 8 electrons in its highest occupied energy level. So if you look here, here we have sodium. Sodium starts with a shorthand configuration of neon 3s1. We have chlorine here. It starts with a shorthand configuration of neon 3s2 3p5. When they form a compound sodium chloride, what happens is that sodium transfers an electron, a valence electron, to chlorine. Now, sodium has the lower energy level has 8 electrons, so it looks just like neon. Now it's Na+. Chlorine likewise has 8 electrons in its outer energy level, so now it looks just like argon. It's neon 3s2 3p6. Now, very small atoms will satisfy the duet rule. They will try to look like helium, but most elements in your periodic table will try to get an octet. So there's 4 main types of bonding, and we're going to be focusing on ionic bonding today, but the next unit we'll be working on is covalent bonding. In this unit, we will also work on metallic bonding, and you'll see covalent network bonding in the next unit. Okay, so the difference between ionic and covalent bonds is that with ionic bonds, this is going to occur between metals and nonmetals. So it's very important that you remember where these are located on your periodic table. When ionic bonds form, we have electrons being transferred between the atoms. Now, for the next unit with covalent bonds, these are going to occur between nonmetals, and they will result from sharing of electrons instead of transferring. So here we have sodium, where sodium is giving one of its valence electron to chlorine. Now sodium has a positive charge. Chlorine likewise has a negative charge. They have opposite charges, so they're attracted to each other, and this is what forms sodium chloride. When this occurs, both sodium and chlorine, like I said, gain a noble gas configuration. When they form the Na+ ion and the Cl- ion, they're very stable and attracted to each other. This is covalent bonding. With covalent bonding, we have, here we might have fluorine, for example. Each fluorine atom has 7 valence electrons. They share one of their electrons so that each fluorine atom then has 8 valence electrons and is very stable when we form Fl2, for example. So this is covalent bonds. So covalent sharing, ionic is transferring. So when we have ionic bonding, metals, these will be losing electrons, and this will result in a positive charge. They become cations. They're transferring those lost electrons to a nonmetal, which gains electrons, and these form an anion with a negative charge. These opposite charges attract, and this is what forms an ionic bond. The reason behind ionic bonding, the reason why this happens, is because of the large difference in electronegativity. So we can actually determine how ionic a particular bond would be by looking at how large the difference in electronegativity would be. So the larger the difference in electronegativity, we see the greater the ionic character of that bond. So if we look at these three compounds here, we have lithium iodide, lithium fluoride, and lithium oxide. We can figure out which one has the greatest ionic character by looking at which one would have the greatest difference in electronegativity. And we can kind of tell this by seeing how far apart they are from each other on their periodic table. So if we look at lithium iodide, lithium is in the second period. Iodine is all the way down in the fifth period of the periodic table. That's pretty far apart. Lithium and fluorine are on the same period, and lithium and oxygen are also in the same period. So in this case, since lithium and iodide are in completely different areas of the periodic table, I would assume that that would have the greatest degree of ionic character. So this would be the one with the greatest would be lithium iodide. Lithium oxide would have the least degree of ionic character because they are the closest together on the periodic table. So an ionic compound, the properties are they're going to be strong. They do not have molecules. So sodium chloride is an ionic compound. And what we see is a crystal lattice where we have the sodium cations, these are positive, alternating with chlorine anions, which are negative. So the smallest particle is called a formula unit. So here's sodium chloride. We have the chlorine ions. If you remember, the anions are larger than the neutral atom. The sodium cations are going to be smaller than the neutral atom. So we have alternating chlorine anions, sodium cations, and this is our crystal lattice. So another way to visualize this is this. And you notice here it has a very cubic structure. It's very has a very geometric pattern to it. And this, if you look at if you look at a salt crystal underneath a microscope, like a grain of salt, you will see it will also have that cubic structure, and that's from that geometric arrangement of the cations and anions. So other characteristics of ionic compounds is they have very high melting points and also very high boiling points. Because you have positive and negative charges, they're also going to be good conductors of electricity, but only when they are able to move, only when those cations and anions are able to move. So we only see this when they're liquefied or if they're dissolved in water. We do not see them conducting electricity as a solid. They do dissolve in polar substances, and we'll go over what polar substances are exactly with the next unit, but water is one of those. So they dissolve very well in water. So here we have sodium chloride. This is a solid. The cations and anions are fixed. They're vibrating a little bit, but they're not free to move. So this is a conductivity tester. And what we have here is we have a light bulb, and we have two wires that are not connected. There has to be something between these two wires to kind of connect that current. Right now, because these charges can't move, that current cannot travel between those two wires. But if we melt this, now those charges can move and they can flow from one wire to the other. And once we hook that this up to electricity, the electricity can flow between there and that light bulb comes on. We can also dissolve that ionic compound in water here. Again, the charges can move. Essentially, these two wires are connected together. And again, when this is hooked up to electricity, the electricity can travel through this and the light bulb comes on. So we call ionic compounds electrolytes. And this word will look familiar to you. So if you've ever had like sports drinks, you'll notice that they talk about electrolytes with stuff like Gatorade. And that's because sports drinks do contain some kind of ionic compound that is acting as an electrolyte in your body, and that helps deliver messages across cell walls. If you ever get dehydrated, your body will start becoming low on electrolytes, and it will be much more difficult for messages to be carried across your cell walls in your body. And then one symptom of dehydration is confusion. You cannot think clearly because of that. The other thing about ionic compounds is they're very brittle. So if you get a hammer and hammer a piece of a salt, for example, what's happening is, let me show you that again. At the beginning, you notice that the positive and negative ions are opposite each other and they're attracted to each other. But when you hit that with a hammer, you notice that now the positive is lined up with the positive, negative with negative, and they repel each other. And that repulsion forces the crystal apart. And so if you hit it with a hammer, it will break into a million pieces. So that's another characteristic of ionic solids. So ionic compounds, you can imagine you have your metal and your nonmetal. So chlorine's your nonmetal. Your nonmetal is stealing an electron from your metal, but they are attracted to each other now because they have opposite charges. So it's kind of like this big dog here steals the bone from the little dog, but then these two dogs are attracted to each other because one's positive and one's negative. So that's just an analogy with your ionic compounds. Okay, so here are just the summary of properties of ionic compounds you should be familiar with. I think all of these you should have in your notes so far. But if you want to have them all in place, here they are. And okay, so metallic bonding is a little different from ionic bonding. With metallic bonding, what we see is we have a bunch of metals, and if you think about your transition metals have a lot of electrons in the D sublevel. Before that, like if you look at zinc or copper, nickel, all those, they only have like 1 or 2 electrons in the S sublevel. So essentially, they have very few electrons in the highest energy level. Because like I said, they only have maybe 1 or 2 electrons in that highest energy S sublevel. What we see then is they also have, sometimes they will have some empty d orbitals, but they will definitely have empty p orbitals. These orbitals overlap, and those very few electrons can actually move up into them and freely move around in the metal. So we say the electrons in your metal are delocalized, and this is why they're very good at conducting electricity. So here is what you can imagine. Here's your metal. And what you can imagine is each of your metal atoms is kind of like a cation here, because its very outermost electrons, its valence electrons, which are the s electrons, are kind of able to move freely in those partially filled or empty d and p orbitals. And then all the atoms are kind of sharing these freely moving valence electrons. So this creates a sea of electrons, and it also enables your metals to conduct electricity. So an analogy here is if you think about each of your metal atoms is kind of like those dogs there in the picture. And if any of you have dogs, you know that they will put anything in their mouths. So here we have the dogs, each sharing their bone, which is their electron, with the other dogs. And then those bones or electrons can move freely between all those dogs, and that helps the metal, in this case, conduct electricity. So these are some properties of metals. A lot of these are common sense. We think about metals, they're naturally going to be solid with the exception of something like mercury. very high melting points. They're not soluble in water. They conduct electricity in any form. That means in a solid, liquid, or gas. Remember, ionic could not conduct electricity as a solid, but could as a liquid. Other properties, they're malleable. Remember, that means that you could hammer it into sheets. Ductile means you can draw it into a wire. And lustrous means it reflects light very well. So these are all properties of metals. Metals don't really bond together, but they do, if we make a mixture of them, they do form alloys. So alloys, remember, from our matter unit, are a homogeneous mixture which contains at least one metal. Examples of alloys are steel, brass, bronze, and pewter. And what this is showing here is that alloys are generally going to be stronger, sturdier than the pure metal. And that's because if you look at the crystal lattice of a pure metal, the different planes of that lattice can slide over each other pretty easily because they're all the same size atom. If you put a different size atom in there, even if it's slightly different, that disrupts those planes and makes them much more difficult to slide over each other. So that's why alloys tend to be stronger than pure metal, and that's why it's advantageous to make them. So these are just two different types of alloys. The first is what we call a substitutional alloy. This just means the two atoms are similar sizes. So we're essentially substituting one atom for another. So an example of this would be brass, which zinc and copper are very similar sizes because they're on the same period of the periodic table. An interstitial alloy has very different size atoms, so these tend to be very strong. An example that would be steel. Different types of gold are going to be substitutional alloys. Okay, so I'm going to stop here for now, and we're going to be going over Lewis dot structures. This will be another screencast, so just make sure you have all the notes from this first screencast.